CirFix, automatically repairing defects in the hardware code. Abstraction. This paper presents CirFix, a framework for automatically repairing defects in hardware designs implemented in language like Verilog. We propose another fault localization approach based on assignment to wires and registers and a fitness function tailored to the hardware domain to bridge the gap between the software level automated program repair and hardware description. We also present a benchmark suite of 32 defect scenarios corresponding to a variety of the hardware project. Overall, CirFix produced a plausible repairs for 21 of 32 and a correct repair for 16 of 32 of the defect scenarios. This repair rate is comparable to that of a successful program repair approach for software, including CirFix is effective at bringing over the benefit of the automated program repair to the hardware domain for the first time. Keywords: CCS concept, hardware, high-level and register transfer level synthesis, bug fixing, software and its engineering, search-based of the software engineering. Keywords: automated program repair, hardware designs, HDR benchmark, ACM reference format. Mhm. Next is introduction. Recent increases in the complexity hardware designs have have challenged the ability of the developers to find and repair defects in circuit description. While significant effort has been devoted to the efficiently verifying functional correctness in hardware design descriptions, relatively little work has been done in patching defects in such description automatically. By and large, de- by and large, debugging and repairing hardware designs remains a very expensive and time-consuming task. Indeed, recent functional and security vulnerabilities due to if defect at the hardware design level had led to expensive consequences. To reduce the cost and improve the maintenance of the hardware designs, a solution needs not only precisely identify sources of defect in real world off the shelf hardware descriptions, but also automatically produce repairs implementing correct functionality of the circuit designs that can be can then be shown to the developers for validation before moving to the synthesis phase. Additionally, we design a solution that applies directly to both behavioral aspect, that is, higher level description of the circuit functionality, and the register transfer level RTL aspect, that is, lower level description of the circuit designs, and it makes use of the ready available resources that are part of the hardware design to validate proposed repairs. The previous work has attempted to address this problem, but may not satisfy all of these characters of the desired solution. For instance, some techniques automatically localize defects in the design source code, but suffer from high false positive rates. Other approaches for automatic error diagnosis and correct require formal specifications to conduct design verification, which usually do not scale to the large designs. Furthermore, previous work does not operate on behavioral level description of hardware circuits. On the other hand, in the realm of the software, significant research effort focuses on repairing bugs automatically. Automated program repair (APR) algorithms fix defects in the software by producing patches that pass all the test cases while retaining required functionality. Traditional APR for software employs fault localization techniques to implicate faulty code, and such techniques are often crucial to the success of program repair. While both software programs and hardware description languages (HDLs) share program uh, languages share programming concepts like expression, statement, and a control structure, suggesting the possibility of the proposing the software repair techniques to the hardware designs. We highlight two key differences between two domains. One, software programs are typically based around a serial execution model, where one line of the code is executed before the next. By contrast, HDL designs are inherently parallel and often include non-sequential statement. Since separate a portion of the hardware can operate simultaneously. Two, software programs usually use test cases to evaluate functional correctness, where individual test cases may pass or fail depending on the quality of the software. HDL design, on the other hand, use test benches, which are programs that with documented and repeatable set of stimuli to simulate the behavior of the device under test. DoT. In both academia and in the industry, the majority of the digital hardware design is done using such HDRs. We present two key insights to bridge the gap between the well-established software repair techniques and hardware design. We first hypothesize that while traditional spectrum fault uh, localization approaches do not apply to the hardware design that feature a more parallel structure. Data flow-based fault localization approaches work well in this domain. Second, we hypothesize that the traditional hardware test bench can be instrumented to admit observed for candidate patches that guide the search for APR. Leveraging these insights, we present a CirFix, a framework for automatically repairing the defect in hardware design implemented in language like Verilog, one of the most popular HDL. CirFix uses genetic programming, an iterative stochastic search technique to find a candidate repair for defect in hardware designs. CirFix also makes use of the readily available artifact in the hardware design process, for example, test benches, simulation environment, to diagnose and repair defect in a circuit description. We propose an approach to guide the search for a repair by instrumenting hardware test benches to record the values of the output wires at specified time interval during a simulation of the circuit design. CirFix then perform a repeat level comparison of output wires against information for respective behavior to assess functional correctness of the candidate repairs. CirFix employs a fixed point analysis of assignment made to internal registers and of wires to implicate statement and reduce the search space, enabling our approach to scale to large circuit designs in industry. We also present a benchmark suite of the 32 defect scenario based on the three hardware experts, two from industry and one from academia, asked to transplant bugs they observe in life into 11 different valid projects. CirFix can produce a plausible repair for a 12 out of the 32 valid defect scenarios within reasonable resource bounds, of which 16 are deemed correct upon manual inspection. The main contribution of this paper are a CirFix, a hardware design automated repair algorithm, a novel data flow-based fault localization approach for HDL description to implicate faulty design code, Another approach to guide the search for a hardware design repair that is compatible with the testbench-based hardware testing process. A new testbench suite of 32 scenarios based on a proprietary bugs but available in 11 open Verilog projects. A systematic evaluation of CirFix on our benchmark suite, CirFix was able to correctly repair 16 out of the 32 available defects under consideration. The two motivating example. In this section, we use an example of the fact from a 44-bit counter with an overflow bit implemented in Verilog to motivate the fault localization and candidate evaluation approaches used by a CirFix. The main block of the source code is shown in Figure 1a with the corresponding test bench in Figure 1b. The circuit design uses wire enable and reset to increment lines 35 to 37 and reset lines 30 to 33, the counter respectively. Incrementing the counter when it has a binary value of 4B111 results into the overflow bit being set to the true line 39 to 41. This implementation incorrectly manages to the overflow bit if the if statement at line 30 is missing an assignment that the set overflow out. Such a defect can have scenarios consequences. The integer overflow errors can be leveraged into significant security exploits. A1 is main block of the 4-bit counter with an overflow error. B is main testing logic from the 4-bit counter test bench. Figure 1, the 4-bit counter with the overflow error in Verilog. For the purpose of this work, there are two key hardware design concepts that we highlight for a general audience: circuit synchronization and parallelism. Circuit synchronization. The main block of the circuit design code shows an orange block, line 727, figure 1a. Oh, sorry. And then they execute repeatedly until the simulation stops. The execution of such a block can only be triggered by changes to wires in the sensitivity list that follows the orange block keyword. Nearly every digital circuit design includes a clock signal, line 50, figure 1b, that oscillates between a high and low state, denoted by event post-H and nega-H respectively. Circuits rely on clock cycle signals to know when or and no and or how to execute their programmed actions. A clock cycle is a period of time it takes for clock signals to oscillate from high to low and back to a high state. For the 4-bit counters in the figure 1a, the wire clock denoting the clock signal is the only wire in the orange block sensitivity list. See line 27. And lines 28 to 42 are executed every time that wire reaches a high state. Parallelism. A key property of HDR designs are not immediately apparent in Figure 1 is that a part of the design code typically executes in parallel. When a design is realized into actual hardware, individual components run all the time. Indeed, every statement in Verilog design not inside a split sequential block of code exhibits concurrency. For instance, for one 4-bit counter in Figure 1a, an implementation managing the overflow bit correctly would include two assignments to a counter out and overflow out on lines 31 and 32 respectively that happen the same time when reset is true. To automatically repair the design code in Figure 1a, CirFix needs to first answer for the original design and each candidate repair what part of the circuit, if any, is being it's behaving incorrectly. Unfortunately, standard spectrum based fault localization tool commonly used by APR for software do not work for eligible designs that exhibit parallelism. To overcome this challenge, we propose the number 40 localization approach based on an assignment to write wires and registers. We first instrumented the existing test bench to record to record the output to record output values at given time interval. This instrumented test bench, when used to simulate the design, reported the output values of the circuit, which can be compared against the expected out. Any mismatch between expected and the actual output serves as the starting point of the for fault localization. For the 4-bit counter in Figure 1, the test bench waits for 10 units of the time before sending the last reset signal. Line 65, the Figure 1b CF stimuli for unit testing software. The procedure block with the test bench that was waiting on the reset signal, line 55, figure 1b, then the set reset to the true upon the next falling edge of the clock signal. This causes any subsequent execution of the corresponding if the statement that reset the wires, line 30, figure 1a, to evaluate the truth branch. Following which the encounter is reset. A correct design should also reset the overflow bit. At this point, the expected output for the circuit requires overflow out to be zero, while the actual value recorded by instrumented test bench is x. The Verilog represents an uninitialized or unknown logic value. This causes overflow out to be implicated for fault localization, and CirFix focuses repair effort on assignment to this wire, and part of the design code that assignment is transitively dependent on, for example, the condition in line 39, figure 1a. For every candidate repair produced, CirFix needs to also answer how good uh, that is fit is the proposed repair at fixing the defect. Unfortunately, evaluation approaches for candidate repairs from software cannot be applied to a HDL description that typically use the test benches. See Figure 1b. So we addressed this using a uh, novel fitness evaluation approach. Our instrumented test bench records the values of the output wires and registers at every rising edge of the clock during an otherwise standard hardware simulation. For developers specify the time interval from the design simulation, a clock cycle by default. Our fitness function compares each output bit against the expected output. For every bit match, we add to the fitness sum. For every bit mismatch, we subtract from the sum. This fitness sum is then normalized. For four-bit counter shown in Figure 1, testbench stimulated the design code for the 26 clock cycles, out of which the first 20 produce an output of X that is uninitialized for overflow out on the original design. This causes an output mismatches for overflow out for 70 clock cycles, resulting into resulting in a fitness score of 0.858. See section 3.2 for surface fitness calculation. A repair managing overflow out correctly would match expected behavior, resulting into a fitness of 1.0. This faulty circuit code was obtained by having a hardware expert from industry adversarially transplant defect from their experience into open circuit description. See section 4. We use this example to motivation to demonstrate the basic design ideas behind the CirFix and an approach that scales well to a large circuit designs as we will demonstrate. This algorithm one is a high-level suffix pseudocode. Technical approaches. In this section, we present CirFix, an automated referring algorithm for defect in hardware design code. Our prototype implementation of CirFix operates on hardware source description written in Verilog. The pseudocode for main CirFix loop is shown in algorithm 1, and the CirFix applies our two-pronged HDR-specific approach to implicate faulty design code and assess the correctness of circuit description to produce repair that can be shown to the human developer for review. Our fourth localization approach simulate a faulty U circuit and assign a blame to an incorrect wire and register output. Line 6 in algorithm 1 says section 3.1. Note that while traditional software-based APR techniques typically compute fault localization once at the start of their search for repairs. We choose to repeatedly relocalize to support multiple dependent edits made to the source code. Our fitness function, tailored to the hardware domain, assigns score to each candidate patch to guide the search repairs. Line 4 and 18 in algorithm 1, see section 3.2. At a high level, Surface uses the genetic program (GP), an, an iterative stochastic search technique to synthesize the candidate repair to the 40 HDL programs. The framework takes as in the source code of implementing a faulty circuit design, an an instrumented test bench used to simulate the circuit for testing and verification purpose, the expected circuit behavior, and the input parameters. The algorithm starts the original source code and maintains a population of the programming variant, each stored as a repair patch, describes a sequence of the abstract syntax tree (AST), added parameterized by unique node numbers. Each program variant is obtained by applying a repair operator, line 12, lines 12 and 16 in algorithm 1, and see section 3.4, or a repair template, line 6 in algorithm 1, see section 3.3, and to a parent selected for reproduction. Candidate variants are selected for reproducing based on their fitness score assigned by the surface fitness function, line 5 in algorithm 1, see section 3.5. Our fixed localization identified code to inserted to or are replaced as part of mutation operations. The algorithm loops for several generations, each maintaining a population of a program variant until a plausible repair is found that produces the output, as observed by the instrumental testbench matching the expected circuit output, or allowed resources are exhausted. That is, the algorithm reaches the timeout or a certain number of generations. For the first For the final post-processing steps, Surface minimized a candidate repair to remove extraneous operations not needed to obtain correct circuit output. Line 19 algorithm 1, see section 3.7. candidate repair and are deployed directly, but are instead shown to the human developers. That is, during the pair process between the artificial design engineer and the verification engineer for validation before the design is ultimately synthesized, reducing maintenance cost. 3.1 Fault localization. Fault localization is critical to the success of the efficiency of the APR. The traditional APR for software often relies on the spectrum-based fault localization to narrow down the defect to certain parts of the faulty program by sampling the program encounter. By sampling program counter. Such fault localization approach do not extend naturally to the parallel structure of the hardware description. To overcome this challenge, we propose another dataflow-based fault localization approach to implicate the fault code in HL descriptions. Previous work analyzing the defect in a large hardware project uh, reported that both defect in the value description correspond to the assignment statement if and if statement. We present an analog algorithm that implements an analysis of an assignment made to wires and registers and a circuit design code to implicate the fault statement. Our proposed algorithm transively captures data and control dependencies in a context-intensive fixed-join analysis, while traditional spectrum-based fault localization approach for software return a linked list of the implicate statement. Our approach returns a uniform length set. Due to the parallel structure of the HDL design, a set of implicate assignments that are equally likely to contribute to the design defect surfaces. Algorithm 2 outlines the high-level pseudocode for our fault localization approach. The algorithm takes as input of AST of the faulty circuit design, the output of the design simulation, and the expected circuit behavior. See section 3.2 for the structure of the simulated and the expected output. If it then compares the simulation output against the expected behavior of the produce a set of the identifier names, that is the variable names, for output wires and registers with mismatched values. Using these mismatches set a starting point for every node in the ASD, the algorithm tests if the node is implicated by output mismatch. Implication of the Implication for a node in an ASD occurs when input data, either the node corresponding to an assignment statement and the left child of the node correspond to an identifier in the mismatch set. CF Data Dependency Analysis. Input and control, or the node that correspond to the conditional statement and an identifier in the conditional statement belong to the mismatch set. CF Control Dependency Analysis. Any implicated node and all of the node children are added to the fault localization set. Additionally, if any child of an implicated node is itself is an identifier, not a part of the mismatched set, the name of the identifier is added to the mismatch set. Add child, for example, for the for-bit counter introduced in section 2. Recall the overflow out wire had incorrect out from the circuit simulation. This causes the wire to be added to the mismatch set. The surface fault localization implicates the only assignment to a overflow out, line 40, figure 1a, by rule, impl data. In the first iteration of the algorithm, indeed, the entire if statement wrapping this assignment, line 39 and figure 1a, gets executed by import control, which brings in the new identifier counter out to the mismatch set as a child. The process is repeated until there are no new identifiers added to the mismatch set, following which the fourth localization set is up. This novel approach to the fault localization for Y hardware is a good fit for automatically repairing HDL designs. It returns a precise set of the implicated AST nodes in a faulty circuit design. Is context insensitive and therefore inexpensive to compute and apply directly to node types associated with ASTs for language like Verilog. 3.2 Fitness Evaluation. The fitness function evaluates the acceptability of a program variant by enjoining a value ranging continuously between 0 and 1 to the variant, with 1 indicate the plausible and that is testbench adequate. The repeat ready to shown to the human developers. The fitness provide a termination of a criterion for CirFix and a guide to the search for unrepair. As mentioned in section 1, the traditional API for software uses test case-based evaluation strategy to assess candidate repair. Hardware designed by contrast use test benches to verify functional correctness. We present another fitness function tailored to the hardware to guide the search for repair to HDL designs. Our fitness function uses key insight, individuality, and comparison. The figure 2 is a comparison between the simulation result and expected behavior information for 44 counter in a mm, motivating example. Wires with the correct output are omitted for space region. Note that the output mismatch for R4 wire 4 times 10^35 through 1 in 95. Traditional hardware benches monitor the values of up wires during the simulation and assess correctness based on the final of up values. For instance, the test bench for the 4-week counter introduced earlier, figure 1b may report to the final values of counter is 5 and the flow bit is 1 when the simulation terminates. Some of off-the-shelf hardware test benches, especially those large projects, may not even report the exact incorrect values, reporting instead merely the presence or absence of an error during the simulation. We want our fitness function to assess a candidate repair based on the intermediary as well as final up values, and assign fitness values to the repair based on its overall closeness to the corrected circuit design. To do so, given an testbench for a 40 HDL description, we instrumented the testbench to the record values of our wires and registers for specified time intervals. This instrumentation is easily automatable, though every hardware testbench must instantiate a device under test (DUT) and connect the wires to the module being instantiated. Cf. Unit test in a software instantiating the object being tested. Each module in turn specified in and output wires, and a static analysis of the instantiate of the DUT can provide the information needed to instrument a testbench automatically. Once the testbench is instrumented, we simulate the circuit design and compare the result against the unexpected the output to the assess to functional correctness of HDL description. We desire a fitness function that assigns a higher level high values to the candidate to repair that display behavior similar to the expected behavior. To do so, we needed to determine the relative contribution of each bit to the fitness of the proposed repair. Given a set of timestamps time, a set of wires, and a registers where a simulation result as time variable 01xg and expected output O time variable 01xg, where x or g correspond to unknown large values and a high impedance respectively for timestamp ci time a set of the time as the element of the time, we'll assume over the n equal is the SCI, the absolute value of the XCI, output bit of the circuit. We compare the expected value for a wire B from a clock cycle CI or CIB or order CIB against the actual value from output O against the actual value from the simulation result as CIB as CIB as C. The figure 2 for an indicative example juxtaposing a simulation result with the expected behavior. And if the bits match, we add the fitness sum of the circuit. If the bits differ, we subtract from the fitness on fitness an additional penalty weight pi is assigned to bits with the values of x uninitialized or g high impedance. The fitness sum SO and the total apostle fitness total SO is defined as follows, where underscore represent a bit values of a 0 or 1. Sum and totals are for the example shown in figure 2, the mismatch X, the X35V and O35V and 0 subtract phi from the fitness sum, whereas the match as 205 and V and 1 and O205V as 1 to the fitness sum with overflow under Y. The normalized fitness of the circuit is then defined as fitness 0 or this novel approach to calculating normalized fitness is effective at capturing whether or not a candidate design is close to the correct implementation of circuit and guiding the search for a repair. 3.3 Repairing template. A repairing template for a defect in a code is defined as a pre-identified pattern that can be applied to some aspect of the code to fix the defect. The idea of using temperature of the API is well studied for software. We applied a repair template to aid CirFix in the search of the repairs. We propose a 9-repair template corresponding to 4 defect categories of HDL design. Of the 4 defect categories we consider, 3 as suggested in the previous work by the Sukta Kurishuna and analyze both fixed history of 4 hardware projects written in Verilog and present several commonly occurring fixes in the 4 HDL description. We propose a remaining defect category based on our experience with defects in hardware design. The repair template in the CirFix presented in Table 1, the incorrect conditionals, a sensitivity list, and an assignment to the corresponding the 3 most commonly occurring defects in the 4 hardware project analyzed previous work. Note that our repair template focuses the correct behavior from the correct circuit design during simulation, cf. rules targeting sensitizability, and for an incorrect condition for a program branch. For example, the condition for a while loop or an if statement, our repairment template can negate the conditioner for an incorrect sensitivity list. Recall that in HDL descriptions, a developer can specify the block of code to execute the infinitely often. For example, line 27, figure 1a, the execution of such blocks can only be triggered by event described in the block sensitivity list. Our repair temperature for this defect categorized can modify a block sensitivity list to a change when the block is executed. HDL designs also allow the use of the blocking and non-blocking statement the for state assignment. A non-blocking assignment statement written in equal must be executed before any subsequent sequential statement. By contrast, a non-blocking assignment written greater than less than equal allows an assignment to be made without delaying the procedure flow of a block. Our repairing temperature for incorrect assignment can change assignment from blocking to a non-blocking and vice versa. Finally, the numeric errors our repair temperature can increment or decrement the values of declared identifiers. Table 1. Repair temperature in CirFix. Defects category. Pattern description. Conditionals. Sensitivity list. Conditioner. Negate the conditioner of a code block. Sensitivity list and assignment and numeric. 3.4 Repair operators. CirFix uses standard repair operators from well-known software repair approaches and mutation and crossover to search the nearby space or of circuit design to produce a repair and avoid local optima during the process. The input parameters multi-threshold line 11 algorithm 1 tunes the relative application of a mutation crossover. As in common software APR approaches, for example, 39 section 3.f is the mutation operator itself can be characterized into three subtypes: replace, insert, and delete. The mutate function of the CirFix framework generates a random probability value and employs the user-defined provided replace, insert, delete threshold. Choose a mutation subtype. The replace operator picks a random node from a fourth localization space and replace the node with another randomly chosen node from the corresponding fixed localization. See section 3.6 space. The insert operator picks a random node from the fixed localization space and inserts it after another randomly picked node within a code block. The delete operator picks a random node from the fourth localization and replaces with an empty node. This operation is equivalent to deleting certain statements from the program variant under consideration. CirFix uses the standard single crossover, which starts by picking a crossover point for each of the two parents. Edit operations to the right of that point are swapped between two parents. This results in two children program variants, each carrying some information from the both parents. The crossover operator plays a key role in avoiding local optima when searching for high-finished patches. 3.4.5 Selection. Automated program repair technique based on GP use selection to choose parent variant from a population based on fitness. The tournament selection, a selection approach that select a random pool of the T program variant in a population and select the fitness member of this pool as a parent, has been used widely for software APR. CirFix uses the tournament selection to select the parent variant to transfer genetic information to the next generation as child variant. The top E fittest program variant from the previous generations are automatically chosen to include it in the next generation in a process known as an elitis- elitism. The fixed localization. 3.6 Fixed localization. Given the fault localization has identified a faulty design code to be changed, our fixed localization provides some guideline on how to perform the changes. While early works on the APR for software choose a node at random for insertion and replacement operations. Such approaches causes a substantial fraction of mutant not to compile. We use fixed localization to restrict the scope of the insert and replacing operators to reduce number of synthetically invalid mutant. For insert operator, we propose to only use statement types, for example, conditional statement assignment and etc. See Annex A64 A.6.4 in the IEEE standard for Verilog for the full BNF definition of the statement types. As a source of the insertion code, we further allow such statement to be inserted only into initial or always blocks, since such statement inserted whereas the violate the syntax of the value. For the replace operator, we design suffix such that an item in a Verilog module can be replaced either another items of the same type or by an internal or by an item sharing the same immediate parent type, as specified in the former syntax definition of Verilog. We observe the our fixed localization approach reduced the average number of the mutants, producing a compilation errors in our prototype of from 35% to 10%. This reduction is comparable to that of the fixed localization techniques in software. 3.7 Repair minimization. During the search of a repair, CirFix might produce edits to the code that do not contribute the repair. For example, repeated assignment statement with an orange block, such edits do not increase the fitness of the candidate repair, but they could introduce an inefficiencies in the final circuit designs or affect the design's readability. Surfaces remove such extraneous edit in the post-processing minimize step by finding a subset of the edit in the repair patch from which no further element can be dropped without causing a reduction in the fitness of the patch. As in the APR4 software, for example, we use the delta debugging the algorithm to efficiently, in a polynomial time, compute this one minimal subset of the repair patch. The minimized set of repairs is then converted back into HDL code implementing the hardware design correctly. The four experimental setup. This section describes the experimental setup for our evaluation of CirFix, including the construction of our new benchmark suite, and our choice of experimental parameters. Table 2. Benchmark hardware project in our experiment. Project and test bench size are measured by source lines of code as reported by the Unix wc command. And our prototype implementation of CirFix, we use open source by P Verilog toolkit version 1.2, 1.2.1 modified the support numbering for each node type to parse a Verilog description of a circuit and produce an AST presenting a circuit design code. We use Synopsys VCS, the primary hardware verification tool used by a majority of the world's top 20 semiconductor companies and to simulate the code using a manually instrumented test bench to assess the functional correctness of the circuit design. Our prototype for CirFix is implemented using Python 3.6.8 and is made publicly available on GitHub. 4.1 Benchmark suite for a hardware defect. For our evaluation, the benchmark suite for a hardware defect. For our evaluation of surface, we desire a benchmark suite consisting of 40 hardware designs that are indicative of defect in industry, comprising a wide range in terms of project size and correspond to a variety of the components found in real-world designs. To the best of our knowledge, there are no publicly available benchmarks that satisfy our requirements. Additionally, there is a limited open-source community support for industry hardware designs, since such designs are often considered the intellectual property of stakeholder companies. As such, we propose to update the defect stating the approach common in software and present a test mark suite for defect scenarios, each consisting of a circuit design, an instrumented test bench for design, information for corrected circuit behavior, and an expertly transplanted defect from real-life experience to be used for the evaluation of automated repair techniques for hardware. The selecting hardware 4.1.1 Selecting hardware project. Every defect scenario includes a base circuit design and a test bench. As you introduce the section 2, figure 1, we require a circuit designed with a available test bench and automate simulation using Synopsys Vicious tool without any change to design code. This is common requirement for common comparable to the testbench switch for API in software. The software hardware project for our benchmark suite are presented in table 2. For each hardware project, we need an instrumented test bench to record output values for a fitness function. While the instrumented process is automatable, see section 3.2, we manually instrumented the test bench for our prototype. Each test bench instrumentation required under 10 lines of developed code, took at most 5 minutes of developer time, and did not require any circuit-specific knowledge besides the information already available in the test bench. That is, identifiers, names of output wires and registers, and the clock cycle duration. We choose 6 projects from undergraduate VLSI courses to be indicative repair of repairing a small component in a hardware design. We augmented this by choosing the remaining five projects from the Open Course, a popular website for open source HDL design. At GitHub collectively to the indicative repairing the entirety of the large circuit design. Unlike some previous works that only use a toy benchmark for evaluation, our benchmark includes a range of project sizes in terms of source lines of code. Any project, including those from courses taught at the undergraduate level, corresponding to a component found in the real-world hardware designs. To satisfy our variety requirement, we include a project from each of the key cores listed in the Open Course website for Open Course certified project. That is arithmetic, communication, crypto, error correction, and memory. 3.1.2 Obtaining information for correct circuit behavior. Circuit surface requires information about the expected behavior for a circuit design to assign fitness values to a candidate repairs. In APR4 software, guidelines for correct behavior often take forms of passing and failing test cases. More generally, however, such information can be induced from a previous version of the design known to be functional, or a combination of data mining and statistical analysis of the design, or manually provided by human developers. This is so-called "oracle problem" remains a challenging issue in general for hardware testing and automated repairing. Implicit, high-level test oracles. The problem does not divided by zero, used by API tools for software to not typically carry over the hardware. Given that circuit design exhibit parallelism and require synchronization against the clock signal. How a circuit design reaches a certain output is often equally important as the actual final output produced. As such, in any hardware test, oracles need to tell the information about the intermediate values from a design simulation, and it does not suffice to only the use output or values from simulation as correctness information for an approach like CirFix. For our benchmark suite, we follow an established approach in APR4 software and employ a previously functioning version of the circuit design to record the expected behavior information for circuit in our benchmark suite. We acknowledge that a such previously functioning version might not always be available, or the circuit specification may have changed. In that case, a developer can use a partially correct or most up-to-date version of the circuit as a starting point, manually annotate the missing or incorrect bits based on knowledge of the circuit design. This process is analogous to the test suite evolution in software. Ultimately, however, if the manual developer effort and previous design are both unavailable, surface cannot be applied to repair defect in a circuit. While Lee recognized the process of annually annotating the correctness information may take longer than manually fixing a single defect, this information is a one-time cost too, as long as the high-level circuit specification, that is, I/O wires and registers, expected behavior does not change. Given the number of the bugs that may arise during the development and maintenance of the circuit design, We believe that it would still be more cost-effective to invest developer effort in correctness information, which can be used by the surface during an expensive machine idle time. See discussion in section 5.1. 5.5.1.3 Transplanting hardware defect. Since actual industrial defects are not made publicly available, we propose an approach based in defect transplantation by expert. Previously was heavily used either randomly seeded or self-seeded defect for evaluation, potentially admitting bias. To combat this, we recruit three hardware experts, two of whom work in the industry and one who works in the academia. With 19 of the years of experience with the hardware design collectively, to transplant, proprietary or non-public, defected from their real-world experience into otherwise correct open-source implementation of a hardware project in our benchmark suite. We desire a defect in our benchmark suite corresponding to a variety of complexities, both in terms of finding and fixing the defect. As such, we define two defect categories for this process. Cate- The Category 1 easy defect denotes mistakes pertaining to simpler, high-level aspects of the circuit design. Category 2 defect denotes more intricate data errors that usually require more effort to diagnose, understand, and/or fix. To get the benefit of the real-world defect in our benchmark suite, we instructed our recruited expert to transplant and categorize real defects, and they have previously encountered the open-source circuit in our benchmark. We also ask our expert for variety of and how the defect appear and would be fixed, as long as the variety of the lines with how often they observed these bugs or mistakes in the real life. We further require we further require that any transplanted defect should compile successfully and change the externally visible behavior of the circuit with respect to an instrumented test bench, and correspond to the approximately same level of the complexity as that of the real-world defect. Table 3 listed the transplanted defect from our assorted data. These criteria, in total, our experimental setup includes 32 different defect scenarios spanning across the 11 hardware projects, with Category 1, that is easy, and 13 Category 2, that is hard defect. This benchmark suit is 1.5 to 10 times as large as benchmark suites used in the hardware diagnosis literature. 4.2 is experimental parameters. We refer to the execution of CirFix as a trial. Each trial is initialized with a distinct random seed for the producibilities of our result, and conducted of the quad-core 3.4 GHz machine with a high bit rating and 16 GB of the memory. We ran 5 independent cyclic surface trials for each defect scenario, stopping when an acceptable repair was found. Each individual trial was terminated after 8 generations of evolution of or 12 hours of work log time, whichever came first. For the GP parameters, we use population size, pop size 500, 5000, and repair template threshold, RT threshold 0.2, with MUT threshold is 0.7, So in line with the established practice from APR for software, we use the deletion, insertion, and replacement threshold of zero point 0.3, zero point 0.3, and zero point 0.4 respectively. For parent selection, we use term size T equal 5 to increase the selection pressure on candidate variant. For elitism, we propagate the top E 5% candidate for each in each generation to the next generation without any modifications. We fit for fitness value evaluation, we use pi equal to as the additional weight as assigned to the bits with the values of x or g. This makes incorrect comparison between the ill-defined wires twice as the detrimental to the fitness score of the candidate repair as binary bit mismatches. We found that a way pi1 did not penalize the such incorrect comparison enough, resulting in a longer time to find a repair, while pi3 caused a significant drop in fitness for candidate variants, negatively impacting the exploration of the search space for a repair. While we leave a comprehensive study of surface parameters sensitivity as a future work, we evaluate our other values suggested by literature. For example, smaller population size and found no significant differences in surface performance. 5. Experimental result. In this section, we present an empirical evaluation surface on our benchmark suite of the hardware defect scenarios. We address the following research questions. RQ1 Research question RQ1: What fraction of defect scenarios can surface repair? RQ2: Does Surface perform better on repairing Category 1 hardware defect compared to Category 2 defect? RQ3 is how effective is the Surface fitness function at guiding the search for repair to circuit description. RQ4: How sensitive is Surface to quality of the information for expected behavior? For a 5.1, RQ1 repair rate and quality for a surface. The repair rate table 3 represents the repair result for each defect scenario. Surface produced a plausible, that is, testbench adequate repairs for 21 over 32, 65.6% defect. Of the 11 defects that were not repaired, 4 exhausted resource limits, while 7 required edits not supported by CirFix operators and repair templates. While a direct comparison between CirFix and APR for software is not possible, we observe that the repair rate of the surface is comparable to the reported repair rates of the well-known software repair approaches, for example, JamPro 52, 52.4% and Angelix 34.1%. When comparing Surface to a more straightforward search algorithm applying to edge at a uniform to a circuit design, and we found that a brute force algorithm did not scale to the complexity of defect in our benchmark suite and reported no pairs with the 12-hour resource bounds. Though not part of a comprehensive scientific evaluation, when tested on a simple single edit defect, not part of our benchmark suite, in a smaller project from undergraduate courses, the brute force algorithm still took hours to find repairs in the surface found in second to minutes, highlighting the surface efficiency pruning of the search space. We leave a full investigation of surface against more straightforward search as a future work. Note that we cannot compare the surface to other baselines for hardware repair, since all the time of the writing, there are no baselines that operate on source code level value description to automatically repair the defect. Indeed, that is precisely the implemented surface brings over the state of the art. The average work clock time for a trial to final repair was 2.03 hours, of which an average of less 90% over 90% was spent on fitness evaluation, that is, design simulation. Most known repair times out after 12 hours, though defect for some projects a smaller search space hit the 8th generation maximum first. These results align previously reported patterns of the behavior for an APR for software, supporting our hypothesis that a surface algorithm is capable of performing as well on hardware design defect as established APR approaches to on software. We acknowledge that work clock long time for surface on a given defect can be longer than that of expert human manually fixing the defect. However, CirFix was designed to favor similar situations in which developer time is significantly more expensive than machine time. It's often more cost-effective to run tools like CirFix using an inexpensive machine idle time, and then to employ the expensive develop time to ensure the repairs are correct before being synthesized, such as we fix surfaces being cost-effective in terms of reducing the burden of designers. Figure 3, uh, representative multi-edited pair by a surface for an defect in the STM controller benchmark. The original defect with the missing and an incorrect assignment is shown in red. The paired code is shown in green. Additional 8 and 9 correspond to the insert and replace operations respectively. Repair quality: We follow the approach taken by Long and Leonard and manually analyzed the 1221 repairs produced by Surface. We found 5 to be corrected and identical to a human repair, another 11 to be correct and different from a human repair, and a final five to be correct only with respect to a test bench, that is all fitting. It's why we acknowledge that having a simple developer manually examine a patch is not a substitute for a true human study on a patch correctness. This analysis adds more some confidence to the majority of the plausible repair from a circuit surface do not overfit to the test bench, a common problem in an APR for software. Since we inspect intermediate wire values when assigning the fitness scores, correctness is critical in hardware designs. For example, since manufacturer chips cannot be easily updated once deployed, and we note that our use case does not involve deploying patches directly, but instead showing plausible patches to developers to reduce maintenance costs. We observed that 7 out of the 12 minimized repairs were multi-edit repairs, highlighting the Surface's ability to produce repairs to be fact to defect that require more than one change to the circuit design. By comparison, common APR approaches for software usually only produce single edit repairs, and only recently have there been works investigating multi-edit repairs. For instance, in a faulty version of the stream controller benchmark, One of our experts changed the assignment to wires transplant a category 2 defect, causing incorrect functionality in post-surface interface. A surface assigned to this faulty design code car fitness values of 0.818 based on output mismatching. Surface is repaired this defect scenario in 4.6 hours by inserting a new assignment and modifying an existing assignment, assignment. The original defect and a repair code are shown in Figure 3. This is indicative instance of a surface repairing category 2 that is hard. Defect in circuit descriptions with multiple edges to the faulty circuit design. The surface produced plausible repair to 12 1 out of 32 defect scenarios in our bench suit, of which 16 repairs were fully correct and 5 were correct only with respect to a test bench, and the surface repairs rate is comparable to the strong result from APR for software, suggesting that our approaching brings the benefit of APR to hardware designs. 32. The architecture the performance of individual defected categories. Surface found a plausible repair to 12 out of the 19 of the category 1 and 9 out of the 13 of the category defect. The average number of fitness proofs for a trial finding a pair to category 1 defect was 1900 and 9500, taking an average work clock time of 2.07 hours to complete. By comparison, the average number of proofs for a trial repairing a category 2 defect was 5,000, taking an average work clock time of 1.97 hours to complete. We found no statistically significant differences in the average amount of time to find a repair between category 1 and 2 defect. Two-tailed man and witness U-test P at 0.373 and suggesting that a defected suffix is able to patch, the repair can be produced in about same time, regardless of the category and therefore difficulty of the defect. The surface repair operators and the repair temperature were particularly successful at repairing defects of the both categories pertaining to incorrect sensitivity list of orange blocks, and the numeric errors in omission of the assignment to wires and registers. On the other hand, CirFix that was less successful to defect scenarios where wires or registers are defined incorrectly or modules are incorrectly instantiated. For instance, a category 1 defect scenarios for the lead Solomon decoder project. One of our experts changed the size of the register to 8 bits before assigning a decimal value of 500 to the register. This produced incorrect circuit behavior since 8 bits are not sufficient to store values of 500. Surface could not produce a repair to this defect scenario, none of which operators pair template, templates are capable of increasing the number of bits allocated to the integer 500. We note that while adding more repair templates can help in such cases, in general, Surface is able to repair both Category 1 and 2 defects with comparable high success rates. Surface perform equally well for Category 1 and a Category 2 hardware defect, adding in confidence that our approach scales well to a variety of defects in hardware design. The Arc5.3 RQ3 Quality of Fitness Function. Surface high repair rate suggested that our fitting function, coupled with with our testbench instrumentation approach, is highly effective at guiding the search for repairs to faulty circuit designs. We observed that for each change to design code that brings a candidate repair closer to a correct repair, our fitness function shows the correctness increasing the candidate repair fitness. That is, our fitness function has a stronger fitness-distance correlation, a trait that makes genetic algorithms thrive. This is best observed in transplanted defects that require multiple edges to a design code to be corrected. For instance, one of our experts transplanted a defect in the counter project that required three edges to the design be repaired. The triple edit repair produced by a surface for this defect scenarios incrementally raised the fitness of the best candidate batch first from 0 to 0.58 and then the 0.77 and finally to 0.12 to produce the correct repair. Similarly, behavior is seen to for every time for every other multi-edit repair produced by a surface, indicating that our fitness function is effective at capturing incremental change to a chain circuit design during the search for repair. We also observe instances of where surface produced a repair deemed fit by our fitness function and instrumented testbench, but considered correct by the original annotated testbench. We examine one such case in detail, related our stage module in the error correction core Reed-Solomon decoder. This module is responsible for generating output bytes from pipelining input memories. A faulty version of this circuit obtained from one of our experts removed the reset wire from the sensitivity list of an always block. This caused incorrect resetting of our output wires by circuit. Our fitness functions assigned the incorrect design code a non-perfect fitness values of 0.999. The original test bench, however, reports no errors in correct code. The final repair produced by CirFix fixed this defect and passed all checks by the original test bench and our instrumented test bench. This suggested that our fitness function and testbench instrumentation can catch errors beyond the capabilities of the original testbench without adding any additional testing logic. The surface fitness function is highly effective in capturing incremental changes to a circuit design code to the guide the search for a repair and has the potential to increasing testing prowess without any added testing loading to a bench. 5.4 RQ4 Sensitivity to correctness information. Since the information for expected circuit behavior is trivial cost for our algorithm, we investigate the quality of the repair produced by CirFix as a function of the quality of this information. We consider the defect in our benchmark suite repaired under conditions where high-quality guidelines for correctness were available. Since repairing the remaining defect with the lower quality information could be attributed to the randomness associated with the stochastic approach. As we varied the amount of corrected information, that is an annotation of the expected wire and register values available from 150, 25%. We observed the number of the plausible repair transition from 21 to 2020, 20 from 21 to 20 to 20, and the number of the to a number of correct repair from goes from 16 to 12 to 10, breaking down the scenarios where only 50% of the correct information was available. We observed that 5 are correct and identical to human repair, and 7 are correct and different from human repair, and the final 8 are correct only with respect to the test bench, including a particular repair to a defect repairing multi-edge to be patched. Note that this is a reduction of 25% in the number of correct pairs when the correctness information is reduced by half. Indeed, of these plausible repairs, a total of 10 were identical to a repair produced under condition when the full expected behavior was available. For the scenario where only a quarter of the expected behavior information was available, we found that 4 are correct and identical to human repair, another 6 are correct but different from a human repair, and a final 10 are correct only with respect to the test bench, including a partial repairs. This corresponding to a decrease of only 37.5% in the number of the correct patches when a correctness information is reduced by 75%. Our result indicated that the repair rate, and more importantly, the quality of the repair produced by a CirFix is not overly sensitive to the quality of the provided respective behavior information. Furthermore, reducing the behavior information does not increase the manual burden of the inspecting produced preserver patches. Since CirFix is only reported the first closure patch it finds, as for example CF, program repair for software, where developers may need to evaluate an increasing number of plausible patches as the quality of the test suite is degraded. This analysis gives confidence that even in a setting where high-quality information for correct circuit behavior might not be available, high marginal benefit and a reduction in maintenance costs are still obtainable from surface. Surface is not overly sensitive to the quality of the expected circuit behavior information, yielding high repair rates and quality, even more under settings where low quality correctness information is used as input to the algorithm. Limitation of the threat, the six limitations and the threat to the validity. Then, our result in section 5 suggests that a surface is highly effective at automatically repairing defects in HDL description. That said, there are several limitations our approach and a threat to the validity of the result that we describe in this section. The timing bugs. First, in the HDL description, stemming from a timing flow issue and an incorrect circuit behavior with respect to the clock signal often go undetected by traditional test bench, requiring instead a complicated analysis of the waveform from the simulation. Such timing bugs are therefore not in the scope of our approach, that heavily relies on test benches and assess the functional correctness of the design. We note that while such bugs are complex to debug, they represent only a subset of the hardware defect in this tree, and a non-trivial amount of defect in the hardware correspond to a functional correctness. Threat to validity: the parameters for a prototype implementation of CirFix are chosen based on implicate performance and may not be optical. We do not, however, that a repair operator's fault and a fixed localization approaches and a representation choice for repair matter more than actual values of the GP parameters for APR. Our benchmark defect may not be indicative of the defect in a real-world hardware project, posing a potential threat to our external validity. To mitigate this threat, we evaluate the surface on a variety of hardware projects taken from different sources and had expert hardware designers transplant defects from their real-life experience with HDL designs covering a variety of the defect types. See section 4.4.1.3. The related work. Automatic error diagnosis and correctness in hardware designs. While a significant of our work has been done in the automatic error diagnosis of the hardware design, the correct of the such errors automatically has not been well explored to the best of our knowledge. The techniques in the works in the Jiang et al. And Lan et al. Employ a software analysis approach to identify the statements in a design code responsible for defect, but suffer from a high false positive rate. Loam and Ottawa use a formal analysis of the circuit description to identify defects, but their approach requires formal specification for large real-world designs that are not always available. Staber et al. Use state transition analysis to diagnose and correct hardware designed automatically, but their techniques similarly do not scale to the real-world circuit with the large state spaces. Our approach, by contrast, is more scalable to large, real-world hardware description. Chang et al. Explicitly insert multiplexer to automatically diagnose faults in hardware designs and suggest repairs. Madre et al. Use Boolean equation solving to diagnose and rectify the get-level design errors. By contrast, our techniques apply to both behavior, higher level, and arterial aspect of a design circuit. Automated program repair for software. In the realm of software, significant research effort has been devoted to repairing bugs automatically over the last decades. Automated program repair usually takes as input source code with a deterministic bug and a test suite with a list. When failing the test reveals the bugs, and aims to automatically generate fixes and buggy code. The test suite bug-based repair, where the test cases are used to guide a search for a patch, can be further divided into generate and validate and semantics-driven approaches. Generate and validate techniques produce candidate patches for buggy code and evaluate them against the test code suit to check if the all test pass. Semantic-driven approaches first extract constraint on a program based on a test suit execution, then they use constraint to synthesize a patch, while the software approach to the APR makes use of test suite and evaluate candidate repair. CirFix uses instrumental hardware test benches to make visible the internal and external behavior of the simulated circuit for fitness evaluation. Additionally, APR4 software usually uses spectrum-based fault localization to implicate faulty code, whereas CirFix uses the Our novel fourth localization approach is supporting the analysis of parallel hardware description. In conclusion, this paper presents CirFix, a framework for automatically repair a defect in a hardware design implemented in language like Verilog. CirFix makes the use readily available artifacts included in a hardware design process. For example, the test benches to diagnosis of the repair defect in both behavior and RTL the designs in the circuit description. These repairs can be shown to the developer for validation before the synthesis phase, reducing maintenance cost. The test-bench-based evaluation and a test parallel infrastructure of the hardware design pose challenges to the render. The traditional APR approaches from software implicable to the hardware domain. We present the key insights to the bridge this gap. First, we propose a method to instrument hardware test benches to admit a circuit behavior to guide the research for repairs. We present a novel finish function dialed to that performs a bit-level comparison to a made visual our wire values against expected behavior to assess the functional correctness of candidate repairs. Second, we present a novel fault localization approach based on a fixed point analysis of assignment made to registers and output wires to implicate statement for defect. Our systematic evaluation of surface present a new benchmark suite of 32 defect scenarios planted by the three hardware experts across the 11 different fellow projects. Such fixed surface produce plausible repairs for 21 out of 20, 32, and a fully corrected repair for 16 out of 32 of the value defect with a reasonable resource bound. Acknowledged. And artifact appendix. Abstraction. We provide a public repository for CirFix for both on Janado and GitHub. The artifact includes the instruction for installing and running a suffix, as well as the script and instruction used to reproduce a score result from our paper. The A1 is artifact checklist meta information program. Python is 3.6.8. PyVerilog 1.211 equals Verilog and uses. Runtime environment Later Linux 7.9. Hardware: Intel quad-core 3.4 gigahertz machine with a hyper-threading with 16 GB of memory. Output: Repair a patch list, that is, sequence of edits to a source code, fixing a defect if a repair is found. Experiment: Running a surface on the defect on our benchmark suite, and a runtime analysis of a surface. How much disk space required? Approximately 5 GB. How much time is needed to prepare workflow? Approximately 1 hour, less than 1 hour. How much time is needed to complete an experiment? Approximately 15 to 12 hours. No longer experiments can be concurrently and override. Publicly available, yes, GitHub repository. Code license if publicly available, MIT license. Archived, provided DOI, available at the Janado. Description: The artifact contains all of the CirFix source code as well as the instruction to install and surface in its dependencies. The README and MD files are root of the repository, and the prototype and type-variable changes directories contain all of the instructions used in the artifact evaluation process. 8.3.1 is how to access artifact. CirFix is available on our Git repository as well as archive on Janado in Appendix 8.2. 8.3.2 hardware dependencies. The output does not have any explicit dependencies. Though older, a slower hardware might take us slightly longer and will produce our result. For our experiment, we used the Intel quad-core 3.4 GHz machine with a hyper-threading and 16 GB of memory. 8.3.3 Software dependencies. CirFix requires Python 3.6.8 and 5, Verilog version 1.21, and Ecars Verilog. It also requires self-sufficient simulator commercialized to simulate the Verilog designs. 3.8.4 Installation. This section assumes the user already have access to the self-sufficient tool. Not Note that the alternative value simulator tools may be used, but would likely require modification to the script to support the API for the simulation tool. Users first need to install Python 3.6.8 and all external Python dependencies, listed under the readme.md file at the root cause of the repository. Some source files value would need to be changed. Support CirFix instructions do not so can be found in a PyValue changes readme.md. Users then need to be configure CirFix to run on a defect on editing the configured file, located in prototype and repair conf. This involves setting the source file, testbench correctness information, and evaluation script path. Users also need to compare the surface GP parameters if necessary. We include our default values in the configuration file. The detailed instructions for a process are included in a readme file located at prototype readme.md. The experimental workflow: after all dependencies have been installed and a configuration file set, users may run the outer Surface script prototype to start the Surface running using the external command python repairing py. The description invoked calls a pipe Verilog to parse Verilog source code into a program AST, which is manipulated to edit the source code. For every change to AST, Surface regenerates the Verilog source code before passing into the Synopsys simulator, which in turn uses the new code and provides a test bench to generate circuit output on a given input stimuli. The produced circuit output is passed back to the Surface is compared against developers' provided circuit behavior information to assess the core correctness of the produced circuit design. The Surface terminates when it finds a design producing output mismatches expected behavior. Users may log the log-tree flag to restore details logged in the prototype repair log detail directory. Era 6 Evaluation and expected result. This artifactor provides instructions for producing the result from the surface evaluation. Every surface execution or a trial that finds a repair to a bug and they will minimize the repair patch list, that is a sequence to edit to the source code that ultimately repair the defect. The repair patch list can be verified against our report result. Table 3 is the raw data included in the prototype experiment result Excel, along with the time to define the repair. We also provide instruction on how to disappear patch list to produce a valid source code for inspection in the file. Note: we hope to maintain Surface as an open source tool. Any issues that are found in the Verilog artifact or any questions that arise can be submitted to GitHub issue on our repository or communicated via email. Okay, thank you. Thank you for your time. I read The Surface Automatically Repairing Defect in Hardware Design.